So to start with today, we're very happy to welcome Samuel Fielding. So Sam is a PhD student studying the real-time forecasting of space weather using machine learning and satellite data at the University of Edinburgh. He completed his undergraduate degree in physics at the University of Sheffield and also an MSc in geophysics at the University of Aberdeen. So Sam, would you like to share your screen and kick off your seminar?
Yep. Okay, let's just find it. There you go.
Okay, great. Go ahead.
Okay, so yeah, my presentation today is going to be space weather, trying to improve ground level magnetic field perturbation prediction. Yeah, I'm at the University of Edinburgh. This is a nice picture of Edinburgh that I've put on the first slide, just to set the mood. So first of all, let's look at the background. So geomagnetically induced currents, they're a major hazard caused by space weather. I've included Faraday's law of induction here in a little bit. And the reason why I include it is because dB by dt is a term within Faraday's law of induction, which is something that we're going to get to later. And it's proving the relationship between the electric field and the magnetic field, which of course has been known about since the 19th century. So obviously GICs are very, very damaging potentially. What you've got is a changing geomagnetic field, and then this induces a current through the ground. The ground has got a significantly higher conductivity than the air, so all of the current will move through the ground, and this will cause basically ground to be different depending on location, and then this will cause induced currents. There's also a portrait of Michael Faraday. So space weather causes these changes in the ground level magnetic field because of interactions between the solar magnetosphere and the Earth's magnetosphere. The Earth's magnetosphere is significantly perturbed by the sun's, and then this causes both stuff in the initial phase. So if you have a solar storm, you've got an initial phase of interaction, and later on you also have energy being released from the magnetotail, and this will also cause ground level magnetic field perturbations. So here's some examples of systems that are vulnerable to ground level, geomagnetically induced currents. So first of all, we've got the national grid and electric railways. So the national grid, for obvious reasons, is a very, very large current system, and transformers can be very significantly damaged by ground currents. We've also got electric railways. So electric railways, there's some thought that you could have signaling errors due to GICs because the signaling basically relies on a current that flows through ground. And when the ground is different in different locations over long distances, this can obviously lead to signal malfunctions. You can have signals remaining on when they should be off, and then this has the potential to cause collisions. We also have long conductors such as pipelines or railway track, and these can be damaged by current flowing through them. So first of all, one of the things I'd like to point out is the unpredictable nature of GICs. So first of all, there's a nonlinear relationship with dB by dt. So obviously this leads to complications in simulations. There's a close relationship with the conductivity of the ground. So if you don't have an accurate ground conductivity map, obviously this will also lead to problems. And it also depends on human conductivity creation. What I mean by this is that the hazards in particular will be reliant on, transformer location, for example, or they'll be reliant on the path taken by a railway through a region. And obviously this is something that you need very accurate data for in order to see the paths of these human conductivity conduits. So finally, we've also got seawater. Seawater can be thousands of times more conductive than just the ground. So obviously, this is because of the ions within the seawater, and that means that you need a very accurate map of the coastline as well. All of this means that it's very difficult to create a really good idea of where GICs are flowing. Oh, sorry, I should mention here, this is Power World. So Power World is a company in the United States that has a simulator for the Eastern United States for GICs. I cannot comment on how accurate it is. The idea here is just to give an idea of what GICs look like when you look at them on a map. So you've got how rapidly the electric field is changing over a distance, for example, on the left, and you've got the actual voltage on the right of the surface. So the main things that scientists aiming to predict GICs are really struggling with. So first of all, there's no accurate estimate of ground conductivity. So if you look at this map on the right-hand side, you can see that this is an estimate, basically, of the ground conductivity in different locations. And we really need a very accurate map because GICs can take place over quite small scales, relatively speaking. And this is something that's being worked on. I have a colleague here at the university that's trying to make a 3D conductivity map of the United Kingdom. Very impressive work. So definitely work in this direction is being done. So hopefully we can solve this fairly soon. And secondly, we've got the fact that there is no accurate method of predicting the intensity or location of induced electric fields. Here's a picture of the Northern Lights. It seems obligatory if we're doing a MIST seminar to have a picture of the Northern Lights. So there's two reasons why this is the case. Firstly, there's no data really on electric current flow, or at least there's very sparse data. So we don't have much training data if we were to predict directly the electric current flowing through ground. This is because we would need essentially electrodes within the ground and then measuring the current distance between them over a massive grid size. And this seems very difficult to do. And the second one is it's difficult to predict geomagnetic activity on these timescales. GICs can take place very, very quickly. And that sort of timescale is incredibly difficult to predict based on data from the L1 Lagrange point. I would also like to say that these two main challenges are both being worked on at the British Geological Survey as part of the Swimmer project. And the hope is to create a really good, basically hazard prediction for the United Kingdom in terms of GICs. So the way to get past this GIC confusion, as it were, is to use dB by dt as a proxy. This is because dB by dt, unlike the electric current or the fields flowing through the ground, is very much less sparse. We've got a network of geomagnetic observatories which are set up over the entire world, and we can use all of that as good data. Here's an example of dB by dt at Tromsø. This was taken last night, I believe, and it's just demonstrating the sort of data that you get for dB by dt at a wide number of observatories. So whilst accurate determination of the exact location and direction may be difficult, dB by dt should provide an indication of areas most at risk. And I think that this is definitely the best that we can currently do. So looking at my project, so the question is, using dB by dt as a proxy, is it possible to create an accurate prediction of GIC activity using the intermagnet network by using physics-informed neural networks? I'll go into some of the work that's been done on this already, and also, can we improve dB by dt predictions beyond predicting the highest in the next 30 minutes, which is the current forecasting ability? So first of all, looking at the input data. So yeah, this is a figure from a paper by Madsen last year. I apologize for the resolution. It looked significantly high resolution when I looked at the slides. So basically, this is data that's been gathered from the L1 Lagrange point. So this is a satellite located in between the Earth and the Sun, upstream for the solar wind. So what we're looking at here is the IMF field, so By and Bz, the flow speed, and the proton density. And these are three very important kind of factors to take into consideration when you're looking at the ground level magnetic field perturbation. So looking at the current progress in the field, so this is a paper by Edinburgh from last year, which was very impressive, and it was predicting spherical harmonics. So using spherical harmonics, can you make a prediction about the ground level magnetic field perturbation from a target station distribution? So you see on the left, this is the supermag stations. And the correct answer is to a degree you can see that there is definitely a predictive capability for Edinburgh's data, and it's very impressive that they've managed to make a spatial distribution map. And if you look at some of the graphs of different locations, you can see that the dB by dt perturbation increases significantly when you look at the start of the storm, which is obviously what we want. We want that predictive capability. However, first thing to notice is that for the second and after that, the phases after the initial phase of the storm, the prediction seems to get significantly worse. It definitely underpredicts. Upendran talks about the too quiet too often problem. So what he's basically saying is that it's quiet so often that it will underpredict when it's not quiet. This is a problem that's been facing geomagnetic predictions for some time. So yeah, it's worse than persistence forecasting if you just look at the absolute error, which is, of course, it's quite difficult to kind of get past that. So then there's also this work, which I'm going to be trying to improve upon, which is looking at the 30-minute maximum dB by dt value. And basically this was done at a number of UK observatories, and it can be expanded hopefully to other observatories. This has got restrictions as well. Obviously, the peaks are not underestimated as much as they were in Upendran's work. This is a positive. This is because the training data was only on active times. However, it will be limited to areas around geomagnetic observatories because it's trained individually on each one, which means that you won't get that map that Upendran was able to make a few slides earlier. And obviously, this is going to be less useful if you look at places that are far away from geomagnetic observatories. And there's no uncertainty in either prediction, which is, of course, a massive negative. So we would like to see some uncertainty in the predictions. So yeah, looking forward, it seems probable that in the far future, I will say, we will have an acceptable model of ground conductivity, and we will certainly be able to improve our computational ability to simulate GICs. When all of this is put together, we should hopefully be well on our way to creating a highly resilient society to this form of hazard. And I think that that's it. Here's my references. Yeah, I'm open to questions on this.